Hello and welcome back to another Chemistry Academy video. In this one I'm going to be going through questions 7 to the end, 11 I think, of the 2022 higher chemistry paper. If you're looking for answers to questions 1 to 6 or the paper 1 multiple choice questions, you'll find those videos on my higher chemistry playlist. So to get started, we've got an enthalpy of combustion calculation here. Now this one is a little bit different to normal because we're calculating the mass of methane burned rather than calculating the enthalpy of combustion. Let's zoom in a wee bit. So we're given a volume of water, a temperature change, which means we're going to have to calculate the energy released. So we do our EH equals Cm delta T first. So you would always do this bit first unless you're given a quantity of energy that's released. If you're given the quantity of energy released, you can just skip this bit and go to the last direct proportion bit that we will get onto. But anyway, so C is 4.18 because we're using water. M is the mass of water, so you need to divide that by 1,000 to put it into kilograms. So 0.1, and then the temperature change is 27 degrees. So put that in a calculator. Times 27, so that's 11.286 kilojoules. So that's the amount of energy we need. So it tells us that the enthalpy of combustion is 891. So enthalpy of combustion, remember, is the amount released when you burn 1 mole. So 1 mole of methane gives out 891 kilojoules, but we are only needing 11.286 kilojoules. So we're going to swap this portion around, but because we're looking for a mass of methane, we need to convert the moles into a mass. So if methane's CH4, it's the mass of 1 mole of it will be 12 plus 4 times 1, which is 16 grams. So we know that 16 grams would give the 891 kilojoules. So we're going to scale to 1 kilojoule. I always just scale to 1 on the side I'm scaling on. So it'll be 16 over 891, and then we multiply up to the amount of kilojoules we need. So it's essentially the same as if using direct proportion if you were trying to work out the enthalpy of combustion, but we're just doing it the other way around. So 16 divided by 891 times by 11.286. So that means we need 0.203 grams of methane to get that much energy. Then bond enthalpy calculation. So I'll get my data booklet up here. But basically you get a mark for retrieving the correct enthalpy, bond enthalpy values. When the equation is like this and it's not written out fully, I would always draw the molecules because you can end up missing double bonds and things if not. So if you didn't get the right answer to this, this is probably why. So oxygen's got a double bond in it, carbon dioxide also has double bonds, and these are the ones that most people forgot, and water looks like that, and there's 2 of them. Okay. So we want to look at our bond breaking. So the bond breaking is always endothermic. You always have to put energy in. Bond making is always exothermic. You always get the energy out. Now I would always write these list headings in your exam because you can pick up a concept mark if you get the calculation wrong, just by showing bond breaking's endothermic and bond making's exothermic. So it's worth just writing these headings down as part of your working. So we are breaking 1, 2, 3, 4 C to H bonds, and again I recommend scoring through the bonds as you go. And then we're breaking 2 oxygen to oxygen double bonds because there's 2 moles of that. Then here we are making 2C double bond O, and 1, 2, 3, 4 O to H. So I'm just going to look up the enthalpy values in the data booklet now. So I've taken the bond enthalpy values from the data booklet, multiplied them out and added them up on both sides. So our bond breaking is a total of plus 2644 and the bond making is a total of minus 3460. Now to get the overall enthalpy change, all we have to do is net these. So 2644 plus minus 3460. And when we put that into a calculator, 3460, we get minus 816 kilojoules per mole. Then calculate the atom economy for the formation of hydrogen. So hydrogen is our desired product, which means we don't really care about the carbon monoxide in this case. So the atom economy is the mass of desired products over the total mass of reactants times by 100. So the mass of desired products is 3 times 2 because there's 3 moles of hydrogen, which is 2 grams each. And then the total mass of reactants, so we've got 1 mole of methane, which is 16, plus 1 mole of water, which is 18, and times by 100. So that is 6 over 16 plus 18, 34 times 100. So we put that into our calculator. We get 17.65%. So that one's one that you could potentially round incorrectly. So just watch out that your rounding's not wrong when you're doing these. Especially if you've got one of those calculators that puts the dot across the top of repeating numbers. That sometimes catches people out. So another naturally occurring gas is nitrogen dioxide. Nitrogen dioxide exists in equilibrium with dinitrogen tetroxide, N2O4. Complete the table to show the conditions that would maximise the yield of nitrogen dioxide. Now you could get caught out here, but nitrogen dioxide is in bold, and if they put something in bold, it means you need to think carefully before you proceed. So nitrogen dioxide is this one here. So we're actually wanting to shift the equilibrium to the left in this case. So if we're wanting to shift the equilibrium to the left, for temperature, we need to remember intendo, so increasing temperature favours an endothermic reaction. Now, our forward reaction is exo, as shown here, which means the reverse reaction that we're trying to favour is the endothermic one. So going this way is endothermic, which means we would want a higher temperature because an increased temperature favours the endothermic reaction. When it comes to pressure, it's to do with the gas moles. So on the left, we've got 2 moles of gas. On the right, we've got 1 mole of gas. Now, for pressure, a low pressure favours more moles, and a high pressure favours less moles. You only need to remember one, and it's essentially just the opposite. I can't spell them right at the same time. So we're trying to favour the side with more moles of gas, so that means we would want a lower pressure, because low pressure would favour more moles of gas. Big Hess's law one here, we've got lots of sub-equations. So I always number them, usually 1 to 3, but we 1 to 5 in this case. And because there's so many of these, it suggests that there's going to be some that are just needed for cancelling. So they can be a bit tricky, but hopefully we will make it make sense. So I always go through the target equation and look for the stuff below, so it's a bit like a terrible chemistry treasure hunt. So we're looking for this chemical here. I can see that's in reaction 1. Now it's on the wrong side, we need it on the left, so we're going to have to reverse this, but we also need 4 moles of it, so we're going to have to times it by 4 as well. So I'm just going to make a note to myself that I'm going to reverse it and times it by 4. Then N2O4, I can see that in equation 2. Now again, it's on the wrong side and we need 5 more moles of it, or 5 moles of it. So I'm going to reverse that as well and times that by 5. The 4CO2, so CO2 is in equation 3. It's on the right side this time, but I need 4 moles of it, so I'm going to have to times this one by 4. Now, H2O is a gas, so this is where state symbols become important as well. That's in reaction 5. So it's on the right side, but I need to get 12 moles of it. So I'm going to have to times this last one by 12. Sorry. Now, the N2 is in this equation here. And for this, it's also actually in equation 1 as well. So any ones in the target equation that appear in more than one of the equation below, I usually just ignore them and trust that it's all going to work out. But because you need 9 moles of it, you can see here you're timesing by 4 and timesing by 5, so that's going to add up to 9 moles of N2 anyway. So it should be all good. Now there's equation 4 here that we've not actually done anything with. When this happens, it means that it's there for cancelling. So if you check on diagonals, you can usually see something that looks like it's going to cancel with, so something that's the same on the diagonal. Now, if we're needing it to cancel with the liquid water, because there's no liquid water in this target equation, then what we're going to need is 12 moles of it on this side, because we're going to soon have 12 moles of it on this side. So we're going to have to times this one by 12 as well. Now, sorry, most people would probably rewrite all these equations, cancel everything out, make sure you get the target one, but I'm just going to trust that it all works out and just manipulate the energies. Okay, so it is a bit of like a chemistry trust fall here. So if we reverse it, it becomes a negative. 54 times 4 is 216. Then that becomes a positive 20 times 5. So that's a positive 100. Number 3, we need to times that enthalpy by 4. So 4 times minus 394 is minus 1576. Then 12 times negative 286 is minus 3432. And then 12 times 41 is plus 492. So now we just need to add them all up. So minus 216 plus 100 minus 1576 minus 3432 plus 492. And that gives us minus 4632 kilojoules. So a very exothermic reaction. Then draw the full structural formula for methyl hydrazine. So this is kind of using your knowledge of valencies. So we've got CH3, we've got an N with an H, we've got another N with 2 H's. And everything's satisfied its valency because carbon needs to make 4 bonds, so it's got 4 bonds around it. Nitrogen's valency is 3, it's made 3 bonds, and again 3 bonds. So question 8, complete the table by circling one option on each line to show the effect of copper 2 oxide on the reaction. So copper 2 oxide is a catalyst, which means it will increase the rate of both the forward and the reverse reactions, but it won't have any effect on the position of equilibrium. So you always get to equilibrium quicker when you use a catalyst, but it doesn't change its position. And you get there quicker because it's increasing the rate of both the forward and backwards reactions. Now, this tells you in part 2, the water-gas shift reaction is exothermic. And wants you to draw a line on the axis below to show how the yield of carbon dioxide would vary with increasing temperature. Now, remember, in Tendo, increasing temperature favours an endothermic reaction. So if you're increasing temperature and your reaction is exothermic, it's not going to be favoured, so the yield's going to decrease. So you just need a line that shows the yield decreasing. as the temperature increases. So it could be a straight line like this, it really doesn't matter, as long as your line is gradually decreasing as the temperature is increasing. Are we limiting an excess calculation? So we've got 7 grams of ascorbic acid, which is the C6H8 one. So I'm going to put M equals 7 grams above that. It's reacted with 250 centimeters cubed of potassium hydroxide. So volume equals 250 centimeters cubed. And its concentration is 0.5 moles per litre. So we can work out the moles of each of these. So if I take their formulas, KOH. So for the ascorbic acid, we've got NM-GFM relationship because we've got a mass and a GFM. And then for the potassium hydroxide, we're going to use the NC-VC relationship because we've got a volume and a concentration. So we've got 7 grams here, 112 here. Don't forget to change your volume into litres. And 0.5. Okay, so we can work out the moles of each. So N is M over GFM. So 7 divided by 112. So that's 0.0625 moles of that. Then N equals CV. So 0.5 times 0.25 is 0.125 moles. Now we take them across and compare them in the ratio. So I'll do it down here maybe. So let's say we want to react all of our ascorbic acid. So it's a 1-to-1 ratio. So if we want to react all of our 0.0625 moles of that, we would need the same amount of potassium hydroxide. So 0.0625 moles of that is needed. Then we look at how much we've actually got. So we've got 0.125 moles present, which means that shows that the potassium hydroxide is in excess and the ascorbic acid is limiting, because we've got more potassium hydroxide than we need, because 0.125 moles is more than the 0.0625 moles we need. Okay, this last bit at the end, the ratio comparison with the wee statement to back it up, is what you need for the second mark. The mole calculations gives you the first mark. Then a bit of numeracy. So a typical drink contains 0.002% of aluminium ferric citrate. A 1% solution contains 1 gram made up to 100 centimeters cubed of solution. Calculate the number of moles of ammonium ferric citrate required to make 330 centimeters cubed of this fizzy drink. So, number relationships we have here. So, it's giving us that 1% solution is 1 gram in 100 centimeters cubed. And then it's giving us a volume of 330 centimeters cubed. So we can work out how many grams is in a solution of that volume for when it's a 1% solution. So if we don't really need to scale down to 1 centimeters cubed, but I just do it all the time anyway. So 1 over 100 and then multiply up to 330. So 1 over 100 times by 330. So that gives us 3.3. So that means there's 3.3 grams in a 1% solution. So that means that if we're wanting this percentage, so 1% solution of that volume would contain 3.3 grams. A 0.002% solution then would be 3.3 times 0.0. I'm the queen of writing and the do not write in the margin, honestly. Let me just move this across. So 3.3 times by 0.002. So even if it was a decimal, you're still multiplying, because if you think if that was 20%, you'd be timesing by 20, so it's still the same thing. So times by 0.002, and that would give you 0.0066 grams. So we're nearly there. It wants us to calculate the moles though. So N is M over GFM. So we know it's 0.0066 grams. The GFM it gave us was 261.8. So if we put that into the calculator, we get 0.00025 moles, or in your calculator, 1, 2, 3, 4, it was probably 2.52 times 10 to the minus 5. Okay, and that's it. You could have potentially done this in a slightly different order, but I have to say this is one of the more complicated numeracy questions I've ever come across. Properties of essential oils, you could have that it's volatile, which means it evaporates easily. That's why we can smell them and they have aromas. Or you could say it's non-water soluble. That's because it's non-polar. It's made up of isoprene units. And you could say that it has a smell, a sweet smell or a nice smell. Or a nice aroma, if that's what you would like to use. Then name the compound formed when isoprene units join together. So that's terpenes, or just a terpene. And then draw a structural formula for isoprene. So I always like to draw this as the skeletal structure because I think it's easier and you won't be penalised for doing so. So it's essentially just a zigzag of 4. By 4 I mean that's a carbon, that's a carbon, that's a carbon, that's a carbon. So that wee zigzag, both ends get a double bond, and then you stick a branch on here. Okay, if you want to draw it fully though, it's got 4 carbons in a chain with again the double bonds here. There's a branch on carbon 2, and then all the other bonds carbon needs to make are to hydrogen. So that would be it there. But like I said, I always find it easier to draw it this way. The number of isoprene units in a zingerberine molecule, you'd think I'd be able to say these names. So the easiest way to work out the number of isoprene units is to count up the total number of carbons and divide by 5, because each isoprene unit has 5 carbons in it. So if you count up the carbons here, you should find there was 15. So 15 divided by 5 gives you 3. Then naming product X. Now when you're naming products, what I always do is score out the stuff that you can see on both sides, because then it shows you what you're left with. So we can see that's the same. Then to these CHs. Then there's that C double bond O. There's a C and an H. A CH. Then CH, CH2. CH2, CH2, CH2. And then you can see what we're left with is H2O, which is water. So I would always advise doing that when you're identifying missing products or even reactants. Just score the atoms that you can see on both sides out and see what atoms you're left with. I'll rub that out now. And then name 2 functional groups present in General and Schogel that are not present in zingerberine. So functional groups we've got are carbonyls, hydroxyls, a double carbon to carbon bond. There's a hydroxyl there as well, carbonyl here. And then if we look at the Zinger bean, it's all hydrocarbon, so it doesn't either of those. So we've got a hydroxyl group and a carbonyl group. The Zinger bean did have the double carbon-to-carbon bonds, so that functional group's not one that's not included. So hydroxyl and carbonyl. Another using your knowledge of chemistry question. This one's on percentage yield. Experimental procedures that could be used to determine the quantity of the product made in reactions such as the examples shown in the table. So if we look at this one first, it's a solid, so we would be weighing the solid using a balance, using the weigh by difference method or using the tare button. And if it's a solid, we would be using the percentage yield equation with a mass, and we would calculate the theoretical yield. So yeah, you're essentially wanting to discuss percentage yield calculations here. For this one, which is a liquid, you would again just do the mass of the liquid. So this is an ester because it's got a Q in the middle. It doesn't say mu. So yeah, for those two, you'd be measuring the mass and then using the percentage yield. For the hydrogen, you could do the same thing as well, measure the mass, but because it's a gas, you could also measure the volume of the gas that's produced and use the molar volume relationship. So this would allow you to talk about molar volume, the fact that regardless of what the gas is, 1 mole of any gas at the same temperature and pressure will occupy the same volume. Normally at standard temperature and pressure, molar volume is 24 litres. So yes, essentially this is an open-ended question talking about percentage yield calculation, how you would weigh a solid accurately, how you could collect a gas, talking about molar volume, and yeah, you could talk about the chemicals that are made, the types of reactions that are involved to add in extra chemistry. So this would be precipitation reaction because you're making a solid. So that means you would have to filter this solid out first and dry it before you weighed it. And then the ester you would have to separate from the water as well, so by evaporation. But esters are quite volatile, so they have lower boiling points than water. And then yeah, this one is the gas you're collecting, so you would usually use a gas syringe. You could draw apparatus and stuff for this as well. It's not the best open-ended question, this one, in my opinion, but so then question 10, a refrigerant is a chemical used in a cooling process. Some refrigerant compounds can damage the ozone layer. Describe the relationship between the formulae of the refrigerant compounds 3, 4, and 5 and their ODP. So 3, 4, and 5. So we're wanting to look at how their structure is changing. So you've got a few options here, but as we can see that the fluorines are increasing as we go down, and that gives a lower ozone depletion level. So the more fluorine atoms you have, the lower the ozone depletion potential. The less chlorines you have, the lower the ozone depletion potential. Or you could say it the other way, the more chlorines, the higher the ozone depletion potential, the less fluorines, the higher the ozone depletion potential. So you can describe it in any of those 4 ways. So I'll just go with the fluorines. So the more fluorines, can't spell, more fluorine atoms result in a lower ozone depletion potential. And it's always a good idea to use the words that they've put in the question for these. You would need to make sure in this one that you didn't say that the more fluorine molecules or chlorine molecules there were, because they're not actually molecules of fluorine and chlorine here. They are just those atoms within a molecule. So identify which pair of compounds should be used to show the effect of replacing chlorine atoms with bromine atoms in refrigerant compounds. So we're looking for ones that are the same, exactly the same, but there's chlorines instead of bromines. So that would be number 1 and number 5, because that's the only difference between them. And then the refrigerants, carbon dioxide and ammonia, have ODP values of 0. Suggest why this is the case. So it's a bit of a strange question, this one. It is a little bit of common sense, but it tells you at the start that the compound, the ODP, is the relative amount of damage that it can cause to the ozone layer. So if it's got an ODP of 0, it must not damage the ozone layer. So they do not damage the ozone layer, and that's why they have an ODP of 0. So you didn't really need any prior knowledge of chemistry for this one, to be honest, which sometimes those ones are even harder because you think that you're meant to have a knowledge of them. Then state what is meant by a free radical. So this is a particle or a substance or a species with an unpaired electron. Substance with an unpaired electron. Again, that's just something you need to get on a flashcard. Then the name given to this step of a free radical chain reaction. So there's no free radical on the left, there are free radicals on the right, which means it's initiation. So free radicals have been made. Write an equation for a possible propagation step. So it's essentially just a pick and mix here, where we pick molecules that we've got given in previous. So for a propagation you need a free radical, so I'm going to pick the F dot. And you also need a stable molecule. So the molecules we've been given are these ones here, so I'm going to pick CH3F. So what happens is this fluorine free radical basically steals an atom off of this one in order to stabilize itself. So if I draw the CH3F out fully, you can kind of see what's happening. So this fluorine atom is going to steal one of these outer atoms and basically swap places with it. So that means we could, if this fluorine was going to take off a hydrogen to stabilize itself, it would become HF, and then we would be left with CH2F dot, because that hydrogen has now been taken off by that fluorine to stabilize itself. So then question C. So we want to know the number of moles of pentafluoroethane, so that's 50% of that mass. So we need to find 50% of 0.05 kilograms first of all. So if we divide 0.05 by 2, that gives us 0.025 kilograms. So because we got the GFM, we can work out the number of moles. So N is M over GFM. We just need to change this into grams. So we've got 25 over 120. And put that into your calculator. 25 divided by 120. Get 0.208 moles. Then fertilizers containing copper 2 ethanoate are used to supply spinach with copper ions. Copper 2 ethanoate can be made by reacting copper carbonate with ethanoic acid. Name the other product of this reaction. So, copper carbonate is a base. Ethanoic acid is an acid. So this means it's a neutralization reaction. Copper ethanoate is a salt. So the other products of a neutralization reaction are water, and when you use a carbonate, carbon dioxide. Okay, that's quite a lot, a bit of National 5 knowledge that they're expecting you to remember there for this one. So yes, just remember, if you're using a carbonate, you'll make carbon dioxide gas when you react it in a neutralization, and the other product of neutralization is salt and water. So then write the ionic formula of copper 2 ethanoate. So ethanoate, if we draw ethanoic acid, the ethanoate is basically the acid with the hydrogen taken off it and the copper put in its place. So if we redraw the ethanoate, so that's the ethanoate there, we've got copper, but this is copper 2, which means we're going to need to have another ethanoate ion on the other side. So if we do that one, that's what it would look like. Again, that's a pretty tricky question, to be honest. So then, a standard solution of oxalic acid can be used to determine the accurate concentration of a sodium hydroxide solution. Given an accurately known mass of oxalic acid, describe fully how 250 centimeters cubed of a standard solution of oxalic acid could be prepared. So this is the standard solution question. So the first step is always dissolve the solid, whatever the solid is. In this case, it's oxalic acid, in a small volume of distilled water in a beaker. Then the second point is always transferring into a standard flask with repeat rinsings. It's the repeat rinsings bit that's important here. And then the last step is to fill the flask up to the mark on the neck. With distilled water. Until the bottom of the meniscus is on the line. You can also add in stopper and invert to mix if you wish, because that is good practice, but it's not always awarded a mark. But you just never know when they decide to change their mind. So then draw a diagram of a pipette. So for this, you need to make sure that you don't close off the end of the pipette and that it's got a bulby bit in it. That's what they were looking for here. And it has to come to a narrower tip as well. But it needs to not have it needs to not be totally blocked off. Okay. And it has to have a mark on it somewhere, just one line. I'm so good at drawing. It's amazing I wasn't an art teacher. So then the indicator used in this titration is phenolphthalein. Phenolphthalein is colourless in acidic and neutral conditions, but is pink in alkaline conditions. State the colour change that would be observed at the end point in this titration. So at the moment your solution is alkaline, so it will be pink, and then when you add the acid, it's going to neutralise it, so it'll become less alkaline, so it should then go colourless once you've added enough acid. So it's pink to colourless for this one. Then state the term used to describe tighter volumes within 0.2 centimetres cubed of each other. They are known as being concordant. That's just a word you need to remember. And then a calculation question to finish the paper. So got concentration of sodium hydroxide solution being determined by titrating 25 centimetre cube samples with 0.126 moles per litre oxalic acid solution. So I'm going to write the concentration of the oxalic acid solution above it, 26 moles per litre. Then it says the average volume of oxalic acid required was 26.75. So again, I'll write that volume next to the oxalic acid. And then wants the concentration of sodium hydroxide to be calculated. So C equals question mark above the sodium hydroxide, and then therefore that's our sample volume, so that would be 25. So if I take the formulas down here, so we've got, that is a bit big, we've got a 1:2 ratio here. I put a plus there, sorry. So 1:2, and then we're dealing with volumes and concentrations, so we're going to have N, B, C listed underneath these. So we're trying to find out that. That's 0.126. The volumes, don't forget to change them into litres. So that'll be 0.02675 for that one, and this one will be 0.025. So we can work out the moles of oxalic acid. Write my calculator again. So N equals CV. So 0.126 times 0.02675. That gives us, your calculators, if it's in scientific notation, will be 3.3 times, or 3.37 times 10 to minus 3. So then if it's a 1:2 ratio, we times by 2 to go across, which gives us 6.74 times 10 to minus 3. So then C is equal to N over V, so 6.74 times 10 to minus 3 over 0.025, which is 0.2696, so I'll just round it to 27 moles per litre. And there's me, the queen of writing in the do not write in this margin. And yeah, that's the 2022 exam past paper over and out. So if you found this helpful, please give it a like. Don't forget to subscribe, tell your friends, and I'll see you again soon.